Okay, all right. So today will be a bit special. We'll not have a regular lectures with slides. What we'll try to do instead is to implement the transformer architecture that we have seen last week. So if you remember what we covered last time, and if I show you that, we talked about attention and the transformer architecture. And that's basically what we'll try to implement today. We'll implement the self-attention mechanism, and then building upon this new kind of layer, we'll implement this architecture. And the goal really is for you to, the goal is for me to show you that it's not that difficult in the end. When we take our time, this can be implemented in just half a day or faster if I don't have to explain that. And at the end of this morning, you will see that we'll have fully implemented this architecture, or at least half of it. We'll just focus on the decoder part to generate data, and we'll also be able to train it live, and I will show you after that if you train longer with a bigger model, you actually obtain something which managed to generate data. Okay? So that's the plan. So most of what I will present will be code in a notebook or in some Python files. So you can just follow along if you want and type what I'm typing or just listen to what I'm saying. Also, please feel free to interrupt. If I'm just coding for 3 hours alone, it's a bit boring for me. So the goal will be we'll start with a small data set of text. And the data set of text I will consider today will be all the books of Harry Potter. Okay, so it's not that long. I mean, it's long when you print it and you have to read all 7 books. But everything can be concatenated in this one big file. And at the end, you see that we have one big text file with about 100,000 lines of text. Okay, and so this is the dataset we'll use, and the goal of today will be to learn not a large language model. It will be a tiny language model in our case, but really the goal for us will be to have a model which, given a sequence of tokens, let's call this WI. The model that we'll want to implement and train today will be a model such that this model will give us access to a probability distribution over the next token, WT plus 1. Okay, so mathematically, the model we'll implement will be a model of the conditional probability distribution over the next words, WT plus 1. When I say word or token, I mean the same thing. Given previous words or previous tokens. Okay? All right. So we'll start simple. First, we'll just prepare the data, and then I will implement a very, very simple model to do that, which will not be a transformer yet, but then we'll change the implementation of this model to make it an entire transformer model. Oops. Okay. All right. All right, so the data we'll be using is this file, okay, which I will load in Python. Is it large enough for everyone to read, or do you want me to increase the font? It's okay? Okay. Okay, so I will open the file, which is there in read mode. And there are a few characters that I should consider. Up. F, then I just say that text equal f.read. Okay, boom. And so already there we have the entire file in just a regular Python variable. So if I show you the first the first 500 characters, you will see the very beginning of the book, and I can print it like this, chapter 1, and so on and so forth. Okay? And in total, if we were to count the number of characters, so I can just compute the length of this variable text, and I have about 6 million characters on which I will be able to train my model. Okay? So there is already a problem if you think about the task that you want to solve in terms of a neural network. We have to start with this piece of text in order to implement this thing. Okay? But if we say that this conditional probability distribution is a neural network, at some point, a neural network cannot take as input words. Okay? It needs numbers. Okay? So the very first thing we'll do is to basically transform each token into a number. Okay? But before, in order to do that, I also need to define what I mean really by a token. So a token will be a way to divide or to split a piece of text into very small parts, atomic parts. And here you have some degrees of freedom. Today what I will do is that I will split the text at the level of characters, individual characters. Okay? But I will also show you by the end of this morning lecture that we can do other kinds of tokenizations. We could have split it at the level of words or some intermediate between characters and words. Okay? But just for the exercise today, I will split everything at the level of characters. Okay, so what are the characters that I have in this text? Well, I can just compute a set over the variable text, and this set gives me access to the entire list of unique characters in the books. Okay, and you see that there are not so many of them. So I will put everything in the list, and I will sort this list, and I will put that in a variable that stores all the characters. Okay, and if I print it, I have this list. Okay, in alphabetical order. Okay, so how many of them do I have? So this is a variable I will keep, which I will call the size of the vocabulary, which will be simply, in this case, the length of this list of characters. Okay, and so now if I print that, let's say I print all the characters, and I print the size. Okay, so I have all 10 digits, all the regular letters from the alphabet, and a few special characters. Okay? So nothing surprising. All right. So this will be my tokens, and I need now to transform these tokens into numbers if I want the neural network to understand them. Okay? So the way I will do that is simply by associating a unique number for each unique character in the vocabulary. Okay, so I will associate to each token. For example, the token about A will be associated to a number, the token B will be associated to another number, and so on and so forth. Okay? And so for that, I will define just a mapping in the form of a Python dictionary, which will map every character S to an integer. Okay, so I will define this mapping as S to I for string to integers. And this thing will be defined as a dictionary for which the keys, they are the characters, and the values correspond to the integers I want to associate to these characters. Okay, and I will define them simply by saying that I will be iterating for enumerate characters. Okay, and now I have in this dictionary, you see for the first character, which is a new line, I associate the value 0. For this other special character, I associate the value 1. For a white space, I associate the value 2, and so on and so forth. Okay? And I will already define the inverse mapping that goes back, that takes an integer as input and decode this integer into a character. Okay? So I will define really the mirror of this dictionary, where I will basically do exactly the same thing, but I will just swap the keys and the values. All right? Okay. And then I will write two very simple functions that will allow me to translate a piece of text into a list of integers, which I will code encode, and I will write a similar function that takes a list of integers and produces a string as output. Okay? So I will define encode as a lambda function that takes as input string s, and then return a list where this list is made of all the integer corresponding to each character in S. Okay. So for each character C in the input string S, what I do is that I return the value associated, the integer value associated to this character. Okay? And now, for example, if I encode some list, some string, I don't know, good morning, I will get as output a list of numbers which correspond to the integer representation of each token. So in this case, each character in this sentence. Okay? And I will write a similar decode function that takes as input now a list, L, and produces as output a string made of all the characters concatenated all together, associated to each integer in the list. All right, so let's do that. So so I need now to use the reverse mapping to go from integers to characters. So for each integer in my list L, I retrieve the corresponding character, and so now I have a list of characters, and if I want to make a string out of that, I can just join everything using this expression. Okay? So if we take this example again, whoops. I have this list, and if I take this list and I try to decode it, I should get back the same input string. So let's see if that works. Okay? Okay. So now that I have a way to basically tokenize my text and then to transform these tokens into numbers, I will just apply this to the entire book. Okay, and I will put everything into a big torch tensor. Okay? So I will import torch. Okay, and I will say that my data is the encoding of the entire text. So text is this big thing that I've loaded at the very first cell, made of 6 million characters. So I encode them all into their corresponding integer representation. And then I put everything into a torch tensor. Okay? And then if I look at the shape and the D type of this, okay, so I get a tensor with one dimension, and on that one dimension, I have 6 million elements, which correspond to the size here that we computed before. Okay? Yes? No, \n is a character in itself. Okay? So that's actually the very first one. So if I go back here, you see that's this first one. Okay, and so now if we look at the same first 500 characters, which were this one, but now in this new representation, we'll get something like this. Okay, so this is what we'll be working with today. We have a list of numbers, and we want to guess the next number. Okay? The fact that these numbers represent tokens now is a bit irrelevant. We can just work at the level of these integers. Okay. So what I will also do already from now on is to split my dataset into two parts, a training set and a validation set. Okay. So I will just take the first 90% of the data set, and I will say this is my training set, and the remaining characters will correspond to my test set. Okay? So let's compute the size corresponding to the size of a training set. Oops, sorry. So I take the 90% of the length of the data. So that gives me 5 millions. And I will say that my training data, is equal to the first n elements of the data variable, and the test set or the validation set will correspond to the remaining part. So everything after n. Okay? And so now I have two data sets. And the first one is made of 5.6 million characters, and the second one is made of 600,000 characters. Okay? Okay, then, so let's think now about the problem that we want to solve. Let's say we are given a window of characters, okay, which I will call either the context or the prompt, okay? And given this window of characters or tokens, we want to predict the next one. So what could be a strategy that we use to solve this problem? So let's say I'm just looking at a context size or a block size of size 8. Okay. And I look at the first block size elements in my training data. So, oops. We'll just do it like this. So I have this list of 8 integers, and the goal is to predict the one that follows, okay, which in this case would be the one we have at position block size. Okay, so given 32, 37, 30, and so on up to 2, we have to build a model that would be able to predict 44. Okay, so what also is important for you to notice is, before we start thinking maybe about a solution, is that actually every piece of text is an opportunity to learn a model. Okay, because if you have a sentence like or a sequence of numbers like this, so 32, 37, 30, 45, 49, 34, 47, 2, and then the next one 44. Okay. So given this sentence made of 9 tokens, okay, we have an opportunity from this prompt to learn the next one. Okay, but actually from the sentence, you have other subproblems that are also packed inside, because from the same sentence, we could also train the model given only the 7 first character. We also need to be able to predict the next one, which would be 2. And similarly, for the first 6 characters, the same model should also be able to predict the next one, 47. Okay? And so on and so forth. So actually in this sequence made of only 9 tokens, we have hidden inside already 8 examples of the task, where we have a prefix, a prompt, and we know the next token which we should associate to this prefix. Okay? So this is something we'll use actually. So let me just... So if I say that X is the first block size element in my training set, and the target Y that I should associate to each of these tokens is just the same sequence but shifted by 1 character. Up, block size plus 1. Okay, so if I print the 2, it says that, okay, given 32 only, I should predict 37. Given 32 and 37, I should predict 30. Given 32, 37, 30, I should predict 45, and so on and so forth. Okay? So this is how we will organize the data. But so just to be fully explicit and to show you all the opportunities to learn this mapping, let's call it T up. So the context in this case would be the first characters up to T included. So in Python, I need to go up to T plus 1. And the target would be YT. Okay. And so in this case, a first instance of the problem would be a problem where the input is equal to the context and the output, or the target, is equal to this. Okay. Okay, so in this sequence, I've hidden all these input-output pairs. Okay? So I will use this actually to already define a function that I will use to make mini batches of data that I will use for training. Okay? Okay. So I will have a function that define, or basically select at random a mini batch of sequences in my training set. Let's call that get batch data. And I will define how many elements I want in this mini batch. So let's say, for example, that the batch size is 4. Okay, and the block size, which is the length of a sequence, will be 8. Then what I do is that I randomly select positions in my data set. So it's any starting position between 0 and the maximum length, okay, which is the length of the data set minus a small margin to account for the fact that I have to read the next block size characters. So it's len data minus block size. And I will be sampling a data set made of batch size elements like this. Okay? So this will correspond to indices. And now I just have to access the sequences at these positions. So my input sequence will be so it will be a list for the index position in the list that I've built before, where I select the segment starting at position I and finishing at I plus block size. Okay? All right? And I will stack all these segments into a torch tensor using the stack function. And for the y values, I will do exactly the same, but shifted by one position, which will be my targets. Oops. So I plus 1 plus block size. And finally, I return these two tensors, which will correspond to my inputs and my outputs for this mini batch. Okay? So to show you an example, let's say I draw a random mini batch xb of input together with the corresponding mini batch yb of output. So I will just call my getBatch function on my training data, and then I can show you the results of these two tensors. Okay, so I have in this case 4 sequences, which correspond to the batch size variable, where we have this input sequence, and then for each token, we associate the corresponding next token. So the token following 77 is 79. The token following this prompt 77, 79 is 76, and so on and so forth. Okay? So exactly as before when I did that for a single sentence, except that now we just do that in parallel over batch size sequences. Okay? And now if we look at all the small supervised learning problems from which I can learn from in this mini batch, there will be many, many of them. But I can do something similar as this, where I will say that my context and my target will be this, but now I have to also iterate over the batch dimension for B in range batch size. This B. Okay, and now from this only 4 sentences, I have all these 32 small supervised learning problems where I know the input and the output that I want to predict. Okay? Do you have questions so far? So we've just prepared the data. We've converted a piece of text into tokens at the level of characters. We've associated numbers to these tokens. Okay, and now I've prepared the data such that we have in a PyTorch tensor examples of inputs which correspond to just a window of tokens. And for each window, I associate the next token I need to predict. Okay, how can we solve this problem? What would be a very, very simple solution that we could try first? Yeah.
For example, if we see that after the 77th token, it's usually the 79th that happens to appear.
Mm-hmm.
We put the 79th token after it.
Okay. So can you elaborate how you would implement that?
If I have this 77 token and I want to know which one is the next one, I just check in all my text, the whole text, how many times which token comes after the most, and I just put the one that.
Okay. So there are two things in your solution which are interesting. The first one is that to predict the next token, you only look at the previous one and you don't consider the one before. Okay, but that's what we'll do, just to start easy. First, and then second, you said you will select the most frequent next token. But to know the most frequent next token, you need to know, okay, in your corpus, in your data set, the number of occurrence of each next token given the current token. Okay, so you need basically to build a big table in which you count, given token 10, in my data set, I've seen that there are 10 occurrences of token 70 that follows, 80 of some other token, and so on and so forth. And once you have this knowledge, then you can select, for example, the most likely token if you want to generate data. Okay? So that's what we'll do, and that's what we call a bigram language model, in which we say it's a bigram language model because we just look at tokens in pairs, the first element and then the next, the first token and then the next. We can extend that later to more tokens if you want, like you can extend that to 3 tokens, and guess what? We get a 3-gram language models. But anyway, that's what we'll do. And you'll see that already we can get results, even though it will be quite bad. But it's still interesting also to basically structure the code that we'll have. So I will implement this model as a regular, as a regular class which inherits from the NN module, which I need to import. Import torched NN as NN. Okay, and as for any NN module class, I need at least 2 elements. I need to define the constructor, and I need to define the forward pass. Okay, so let's do that. So that will be my constructor in which I call the parent. Like this, and I will do other things later. And the forward pass is just a function that takes some input and we'll have to produce something as output. Okay? All right, so what do we need? If you want to implement this bigram language model, we need this mapping. We need this some structure that will memorize for each input token the number of occurrences of each next token. Okay? So we can do that using simply a table. And so I will call this table my token embedding table, which will be implemented as an embedding layer from PyTorch, which is what? Which is just a big hash table or a big dictionary where you need to specify two things: the number of unique input values, which in this case would be the size of my vocabulary, because I have as many first tokens as I have unique characters. And for each, I need to store a vector of counts, and the size of the vector of counts is also the size of the vocabulary. Okay? So effectively, this embedding layer is just a big matrix in which I will have some inputs. So this will be V, the size of the vocabulary. I have some input token at position I. And I associate to this input token a vector which is also of size V, the size of the vocabulary, such that each position J in this vector corresponds to the number of counts, the number of occurrences of the next of that next token in my dataset. Okay? Okay. Well, except that I don't want to count. Okay, what I want, of course, is for the neural network to learn directly this mapping. Okay, so I will just say that I associate to each character, to each token, a vector of probabilities. Okay, which will correspond to this vector instead of counts. Okay. And I will let the network learn the content of this vector. All right? So this token embedding table will effectively just store real values. Okay, so they are not proper probabilities, but they will basically just correspond to logits, exactly as we have seen before when we consider the sigmoid activation functions at the end of a classifier. What comes in as input is what we call a logit, or the same for a softmax function. Okay, so the logits would be equal to the evaluation of the embedding table at X. Okay, so what I will also do today is I will try to consistently show you the shape of everything we are dealing with. So X typically will be a tensor with a batch dimension B and a size T. Okay? And the logit will be computed based on this input tensor. And what will be the shape of that? So we'll just associate to every token in X. So F for every value in X, and we have B times T unique tokens in X, will retrieve the corresponding embedding in the table. Okay? So logits will be a tensor of size B times T, and then for each token, we'll retrieve a vector of size V. Okay? Then I return this. All right, so let's instantiate this model like this. Yeah, maybe I will just pass also that as input. All right. So if I evaluate now in my model on my mini batch, and I look at the content, of course, and then it's not defined. Yeah. Like this. I have this big tensor as output. Okay. And you see that indeed, if we were to look at the shape, we have a 3D tensor of size 4, because B is equal to 4, times 8, the length of a sequence, times 104, which is the size of the vocabulary. If you remember, that's something we've computed there. Okay, we have 104 unique characters. Okay, and the content, so if I take, for example, this one, so for the first sentence, now I have 8 times 104 elements. Okay, and it just say, for example, if you look at this first row, okay, you associate this vector of logits for the first token, and this vector of logits is something we'll interpret as something we can use to derive a probability over the next words. Okay? Okay. So we've not trained anything yet, but still what we'll look at now is that can we already use that to generate data, to be basically sample next words computed by this bigram model given the current words. Okay, so to do that, I need to add a new method to my model, which I will use to generate data. And I will define a function that will take a prompt, X, or several of them together already in a batch, and will continue these sentences by adding a certain number of new tokens. All right? And what I will do is, so let's say I have to generate 10 new tokens. So max new token is set to 10. Well, I will start from the current prefix. I will sample the next tokens for each of the rows in my batch. Okay, using these logits. And then I will produce a realization out of this distribution that will produce characters, which I will concatenate to X. And then I will iterate like this, max new token times. Okay? Yes, you had a question? Not yet. No. The logits, they are really just real numbers that we can make into probabilities. For example, that's something we'll do. We'll just pass this value into a softmax, and then that will become probability values. All right, so let's do that. Sorry. So I will have a for loop, and I will iterate max new token times. I will compute the logits for the current value of X, okay, by just doing a forward pass on X. Then these logits, they give me this vector of probability values for each token in X, but if I want to continue, I just need to access the logits associated to the last token of these sentences, right? So if you remember, logit is this 3D tensor. What I need to do is to only access the last element along the time dimension and to select all entries also for the next over the vocabulary dimension. Okay? So these are the logits that you associate to the last token of each of the sentence. Okay, and now we need to make these numbers into probabilities. So we need to transform these logits into probabilities. So the way you can do that in PyTorch is by using eft using the softmax activation function, which is defined pour torch. Functional as f, right now. And now I can just do this. So the probability values that I will compute from the logits will be the softmax activation of the logits, okay? And I will do that over the last dimension, okay? Which in this case is the first dimension, it's the dimension 1, okay? So again, let me just write the shape of everything. So now, so x x is b times t, okay? Then we do the forward pass that to produce the logits that produce b times t, a tensor of shape b times t times v. Then we only select the last element along the t dimension, so that becomes a tensor of size b times v, right? This one does not change the shape. Okay, we've just transformed the values inside the tensors into probabilities, but the shapes, they remain. Next, we'll draw the next characters for each of the B input sentences. And we'll do that. So we have basically now probability values that correspond to a categorical distribution over the next characters. Okay? So I can just use a multinomial distribution parameterized by these probability values, and then I draw random values out of that. Multinomial. Props, and I say I want one sample for each of the probability values. So now this corresponds to b times 1, where 1 corresponds to the number of samples. Here I've set. And finally, I can just concatenate this x next with x, like this, and I will concatenate along the last dimension, or dimension 1. Okay? And then when the loop terminates, I just return x as output. Okay, boom. Okay, so now if I do lm.generate on xb with max new token, so I have 8 tokens initially, and I say that max new token is, I don't know, 1. Okay, now I have this as output, so it's the tensor where we still have the same number of input sentences, 4, but you see that now we have sentences of size 8 plus 1, because we've added 1 new token. Okay, but we can generate many more if we want, like this, and we would have much longer generations. Okay? Does that make sense to everyone? Okay. So let's see if these tokens, they do make sense if we decode them back into characters and into strings. So I will start from just a torch tensors made of 1, 0, 1, 1, like this. Okay, max new token. I got 10. Oops. Yes. Because when you instantiate a matrix like a tensor with zeros, it's float by default. So I need to say this corresponds to integers. And I have something like this. Okay, so this is just an example of one random generation, starting from token 0, which is the new line, and then completing for 10 more characters. So this should be of size 11. Yes, 1 times 11. Then I will be selecting that single element, okay, to have a flat tensor, which I now transform into a list. Okay, I have this. And now that I have a list, I can feed that to my decode function. Okay, so if you initialize randomly this bigram model with random values in the logits, in the embedding table, and you generate sentences at random, this is the kind of thing that you get. And we can generate longer sentences if we want. So, what do you think about the quality of these sentences? Pretty bad. Why? Yeah, there is no I mean, just random characters without any attempt to be coherent from one character to the next. But it's expected because we have not even optimized this guy. Okay? So that's what we'll do now. So we'll use Adam for the optimizer. Okay. What are the parameters I should train? That's what I need to pass to the constructor of the optimizer in this case. Yes, so lm.parameters. I will set my learning rate to some value like this. Then I will have my training loop. For step in range 10. So let's say we just make 10 iterations for now. What do I need to do at each iteration? I need to get a random mini batch from my dataset. Okay, that's something I've already prepared before. And then I need to evaluate some loss and to optimize it. Okay, what would be the loss I could optimize if I want to train the logits such that eventually I can convert them into probabilities over the next words, or the next tokens? Okay, so what we have is, so we start from a prefix like this, a prompt like this, and we have to predict one of the possible next words. Yeah, so that's just the classification problem, okay? And if you have to solve a if you want to train a classifier, we just use the cross-entropy loss, okay? So that's what we'll do. So I will compute the logits as the output computed on the inputs, the output of the language model computed over the inputs xb. So this is something of shape b times t times v. Okay, that's something I will need to extract out. Okay. Then if you want to use the cross entropy, you cannot use the cross entropy. I mean, it expects at least a flattened list, but in our case, we have the b and the t dimensions, and then it's only after these two that we have our input and output targets. So I need to flatten the two first dimensions for the cross entropy to be something that we can evaluate. So I will transform this into by using a view where I flatten the first dimension, the first two dimensions, and I keep the last one. So now logits becomes something of a tensor with two dimensions, where the first is equal to the product of the first two originally, and the second is V. Okay? Then the targets, while they correspond to what I have in YB, but again, I need to flatten this thing into now just a big list of B times T target values. All right, and now that I have this, I can evaluate the loss, which is the cross entropy, okay, as also defined in the functional module, where I have to pass first my predictions in the form directly of logits. I don't need these values to be probabilities, actually. You can just feed directly logit values, and together with the targets. Okay, so now that will give me some number. The next thing I need to do is to actually compute the gradients, and then to make a step to update my parameters. Okay, so first thing, I reset my gradient. I do a backward pass to compute the gradients, and then I make a step. Okay? And then at the end of the loop, I will plus the value of the loss. Okay? So that works. And so I'm just training manually here. But I could repeat that many, many more times. Let's say 10,000 times. And now we have a loss which has decreased, so something has been learned. So let's see now if we have better results when it comes to generating sentences. So I'm just reusing the code from above, but now the LM model has been trained, at least so what we have trained actually is the content of this embedding table. Okay, and we have trained it such that it from the current word, you associate a high probabilities to the next word you have seen in the training set. Okay? And you do that through the cost entropy that you minimize. Okay, so what do you see in the generations compared to the one above? Maybe I should print. It will be better. Why does it look like text? Yeah, so even though it's still something we can't read, already what you start seeing is that characters, letters are grouped into words, even if these groups of letters, they don't mean anything. And in between, you have spaces, like what we are used to. You also maybe notice that if you compare with the generation above, there are many occurrences of special characters which are actually quite rare in a regular text, and you see them. Much fewer of them in this generation, because also now you have associated a much lower probabilities to these special characters. Okay, so the frequencies already are quite good now. We have common letters which appear often. They are grouped together into something that maybe looks like words. You also see that there are very few uppercase letters. compared to lowercase letters. Again, it's because the frequencies now, they are much better captured. If you compare to that, you have a mix of everything, special characters, uppercase, lowercase letters, and so on and so forth. Questions on this? Okay, so let's take a break then. We'll resume in 10-15 minutes. What I will do is that I will put now everything into a regular Python file, and then we'll improve this model starting from there. Okay, so we'll continue with the implementation of the transformer. So far what we have implemented is a very simple bigram language model, but really you'll see that the structure that we have used so far can be quickly adapted to the entire transformer architecture. So I will switch now to another file, or maybe I will do it here. GPT. Okay. All right. Okay, so this is basically the same code as we have written together, but everything gathered into a Python file, where you see all the imports, some of the hyperparameters, like the batch size, the block size, the number of training iterations, some learning rate. Then we open the data from the same file as before. I've just basically copy-pasted everything. I have the same encoding, decoding functions. I split my data set. I have this function to retrieve random mini batches of sequences. Then I have the same bigram language model as the one we've implemented. We just have a big token embedding table, which associates to each token a vector of logits, from which we can derive the probability values for the next token. Then maybe the only difference is that I've put the loss directly now as a method of the class, which takes as input some input and targets, and then evaluate the cross entropy, but otherwise it's what we had written previously in the training loop. I have the same function to generate data, so to continue sequences. Then I instantiate my model, and then I have the training loop using Adam, the learning rate, and I iterate for max iterations over mini batches. I evaluate the loss. I do the backward, and then I make a step. Okay? And finally, at the end there, you see, so there are these 3 lines of code to continue a sentence that would start with the letter or the character H for 100 new tokens. Okay? So if I execute this, let me do it like this. So this file, which one is it? So this is today's version. Okay, so you see that we get the same kind of output as we had before. It's still random, but we start in some structures about aggregations of characters into words. We see more or less the correct frequencies or marginal frequencies of the characters, but it's still very far from being a good language model when it comes to the quality of generations. All right. Okay, so now we will continue and improve the script. So there are a few things I will implement because they will become convenient later, but I will already do that. The first thing is that this implementation by default run on a CPU, okay, which can be quite slow. So what I will do is make the changes to have a model that I can train directly on the GPU. Okay, so this will be running on a machine with GPUs. All right. So the way you should do that in PyTorch is first by checking if you have access to a GPU. In which case I will call the device CUDA. If torch.CUDA is available, like this. Otherwise, you fall back to the CPU device. Okay. I will add a print just to check when I execute this script which device I'm actually using. Up, like this. And that's it. And now, of course, if you just say that, nothing will happen. You will just have stored the string in a variable which is called device. You have to do the transfer of the data onto the GPU. And so there are two things that we should transfer onto the GPU. The first one are all the data itself, or specifically the mini batches that we create. We should put them onto the GPU. So that's something we can do quite easily by just saying that X, Y are transferred each to the GPU or to the device that we have access to, like this. All right. So now, every time you call this get batch function, that will return a mini batch, which already will have been transferred to the GPU, if we have one. I should also move the model itself to the GPU, like this. Yeah. And when I generate, I need this guy also to be on the GPU. Okay. Sorry. So hopefully this should still work. But now you see that the device that has been selected is CUDA. It's not necessarily much faster for this case because we have a very small model. So you have a very small gain by going onto the GPU. But as soon as we'll consider much larger models with tens of millions of parameters, that will become something really important. Okay, so that's the first change. And the second change will be also to evaluate, as I train, the quality of my model. So I will slightly modify the training loop. So I will define an evaluation function that will take as input my model, and then we'll just make a few prints. And what I will do is to basically evaluate the loss on the training set and on the validation set. Okay? You could say, but I could just have used this loss that I compute at every step. Okay, but this is a very noisy estimate of the training loss because this is only computed on a mini batch. So it's always a good idea to have a proper evaluation function which will reevaluate the quality on the training set on many more mini batches than just one. Okay. Okay, so I will basically compute several statistics, which I will store into a dictionary that I will call out. And this is what I will return. Okay. Every time also you evaluate, a good practice is to switch the model into evaluation mode because there are several layers that need to be switched to the evaluation mode, like the dropout layer, which is something we'll see later on. But if you don't do that, then you will get random outcomes. And once you have completed the evaluation, then you switch back to a training mode for the model. And that's something you can do by invoking eval and train onto the model to switch from one to the other mode. Okay? All right. So now I will have a for loop over the training set and the validation set. Okay, so I will have first the training set, my train data, and second element, which will be the validation on validation data, like this. I will compute several times the losses over a certain number of mini batches. And this number of mini batches is a variable that I will call evaliter. So number of iterations, the number of mini batches for which I want to compute the loss. And I will store all these values into just a tensor. Okay, so evaliter is a new variable that I will add there. Let's say I will recompute the loss over 200 mini batches just to get a good and stable estimate of the actual loss on this data. Okay. And then I just repeat for k in range evaliter, bim. I get a mini batch over the data, which could be either the training or the validation data, depending on the iteration for the outer loop. Then I evaluate the loss over x and y. Okay, so this method loss is just the code that we had before, but which now I've put there. Okay, and you see why it makes sense to have factored out this piece of code, because if I had left this piece of code there, I would have to write it there in the training loop and once again in the evaluation loop. Now I just have it once at this position. Then I store the result. Oop. And finally, I say that for the value train or validation, which is stored in the split variable, I return the mean value of the losses. Okay? And then one small optimization you can also do is to say that this function should be run without gradients, so in no grad mode, so to avoid the creation of the graph of computations. So that will be faster if you just do this. Okay. So now that you have this function, we have to add it into the training loop. But of course, this function will take some time to run, because for each call of the evaluate function, we'll need to iterate 200 times, twice over the training and the validation set. So that's not something you should do at every step of the optimization. Okay, so that's something I will do only every once in a while. Okay, so if I is eval_every, well, this will be a new variable which I will put there. Let's say I will evaluate my network every 250 updates. Okay, then I evaluate the model that returns this dictionary where I will have the mean of the training loss first and the mean of the validation loss. And I will just print that just to have some idea of whether the training is going well or not. Okay? So the current step will be this. So we have first the training loss. Then second, we'll have the validation loss. Okay, and what do I need to print? So the content of the dictionary for the first key. So it's train, and I will just format that as a floating numbers with 4 digits after the comma. And I will do the same for the validation. One, two. Okay, so let's see if that works. Okay, so now you see once when it is training, we have these additional messages. So every 250 steps, we see the training loss and the validation loss, and we see that indeed, as we train, the validation, both the training loss and the validation loss do decrease as we expect. Okay? Do you have questions so far? Okay. Okay, so now let's see how we could actually improve so now basically all this code is mostly boilerplate code that we need to write once. Now we'll focus on the interesting bits, which are about the model. Okay, but everything around will basically remain the same. I will not make any change to everything else. We'll just make now the language model better. Okay? All right. So the first thing I will do is to remove this thing, which is data dependent. I will just have it defined. Where is it defined? Vocab size, it's there, so I don't need to have it. All right, so the very first thing I will do is instead of mapping each token directly to a vector of probabilities or logits, I will go through an intermediate representation, okay, which I will call an embedding, which will be vectors. And then I will have then another layer that goes from these embedding vectors to probability vectors. Okay? All right, so let's do that. So I will have a new variable here, which I will call the embedding size, which I will set to, let's say, 32. In the course, this variable is what I name D in the slides, or very often it's also called C in the literature. Okay, it's just basically the size of the vector representations of your token. Okay, so that means now I will not any longer associate to each token directly a vector of vocab size. I will associate instead a vector which size is the size of the embedding. Okay? So now that means the forward there does not return any longer something of size V, but of size C. All right? But then I need a new part that would go from these vectors of size C up back to vectors of size V. Okay? And I will do that very simply by adding a new layer, which will be just a linear layer that goes from vectors of size C or an embedding to vectors of size V. Okay? And I will call this the head of the large language of the model, which is basically, if you maybe remember this slide, it's this one. Okay? It's the one that we have above that goes from tokens of some fixed size like C, and then expands that back to the size of the vocabulary. So this LM head will exactly be this layer that we have above in the decoder. Okay. So this is a linear layer that goes from input elements of size n embedding and produce output elements of vocab size elements. All right, if I'm not mistaken. Yes. Okay, so then that means we have to change also the implementation of the forward pass. So this now will not directly correspond to the logits anymore. This will correspond to the embeddings of the tokens. So let's call that toc embedding. If I want then to use that to produce logits, I need to call the head of the model. So lm head on what? On toc embedding. All right. And so now we have something which should be of size b times t times v. And if we okay, so let's see if that works. Okay, of course there is a mistake. Yeah, this one I can remove. Okay, so that works. And you see that already with this single modification, we've just said that we are transforming the token into some intermediate representations, from which then we'll compute the vector of probabilities. And you see there already that the loss is lower than before. Why? It's because now you can, two tokens, two characters that would be different could be mapped to vectors, embedding vectors that are close to one another, such that when you pass these vectors to the head, they are mapped to the same vector of probabilities. Before, this could not happen because we were associating unique probability vectors for each unique token. So now we are able to exploit knowledge if two tokens basically are similar in a way or are always followed by the same other tokens, then that's something that can be exploited by this network. Okay? All right. Next thing is to add the positions. Okay, so if we look back at the architecture, you see that also when we are dealing with tokens, there is this part below, where we say, okay, we have the embedding of the tokens. That's what we have just actually implemented also. But we have this second part, which adds some positional encoding, okay, onto the representation of the tokens, okay? Because the token by itself does not know where it is in the input sentence. Okay, just a token that you associate, for which you associate a vector, but there is no information about the position of that token in the original sentence. So that's something that we have to add explicitly if we think this is useful. And so what I will do is that I will create a new table, a position table, which will give me a vector for each possible position of a token in a sentence. Okay, so in my case, if I say that I have prompt up to size block size, so if the maximum length of a sentence, of an input sentence is block size, that means I have at most block size positions of a token within this, to which I will associate a vector of size n embedding. Okay. I can similarly compute the positional embedding in the forward pass. Okay. What I will do there is a bit different because I will not directly pass X, I will just pass the positions themselves. Okay. So here I should call the position embedding table, for which I evaluate torch.arrange t. So I just have a vector of numbers from 1 to t, which I get with the arrange function, where t is the size of x. And I put that on my device also, otherwise it wouldn't work. Like this, but we don't have t, that's something we need to extract, and we can do that from the shape of x. All right, so how do we add this positional embedding? Well, really what we do is just to sum the two representations, to sum the two vectors. So we'll be summing the token embeddings together with their positional embeddings into a new vector, and then we'll pass that to the head of the model. So I will just say that H now is the sum of the two. Okay, and then instead of passing the embedding of the token to the head, I'm passing H instead. Okay. Should work. There is another modification I need to do. Otherwise this thing will fail. So I need to, when I generate now, because of the positional embedding, I cannot handle sentences that are longer than the maximum size. Okay, so if I want to generate actually longer, I need to crop the prompt to only include up to block size elements. Okay, so this is what I will do there. So I select all the batch elements and then I keep the last block size of them. Like this. Then I call the logits on the crop. Boom, 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 boom. And then I concatenate. That's okay, I think. So let's see if that works. Oh, it's not this one. So it's still a bigram language model, but it's already a bit different because now a token also knows its position. Okay, and so here it does not translate to a lower loss, but it should be already more powerful than before. Okay, next. Okay. So there, I will also compute the number of parameters because that's something then will increase later on and can be useful to monitor the number of parameters we actually have in this model. Up. Parameters. Okay, so how do we do that? So you have access to this element in any neural network model. So any class that inherits from the NN modules implements by default these parameters method. So that allows you to iterate over the parameters. So for P in, and then I will just be summing them. So I counting the number of elements in each of these parameters, where a parameter is like a tensor, which is made of many, many elements. And then I sum all these values like this. Okay, and this will be like this, should be okay. Okay, so you see that in this very simple model, we already have 7,000 parameters. Okay, and the parameters here are the mapping that goes from one of the possible 104 tokens to a vector of embeddings of size 32, if I remember. And then you have the linear layer, the head, and also you have the embedding table for the positions. Okay, but in this case it's very short. We have only block size of them, so 8 of them. Okay. Okay, so I will also continue preparing the script to monitor everything. And something I really recommend you to do when you actually implement one of these neural networks is from the start to make everything ready to be monitored on a platform like Weight and Biases. And you will see that it's very convenient, and you should not wait for the end of your project to do that. It's something you should do very early. So that's something I will do as well. Okay, so yes. So I will show you. It's a platform. It's a website basically that. So instead of printing everything like here in the terminal, you can basically that might be enough for one simple run. But when you will have, for example, to do hyperparameter tuning and you want to study different variations of your model, you want to have all these results summarized and stored properly. And that's something you can do with weight and biases. So this is this platform. And you will see that everything that when we run the script, everything will be logged directly onto this platform. And directly for you, you will have access to the training losses without having to do any plot, for example. Okay, so I will show you that in just a minute. So I import 1db, then below the hyperparameters, 1db. So I initialize the thing. I will store everything into one of my projects that I've called NanoGPT. And I will store the config. So basically what will happen is that every run you do will be stored on this platform, and everything here will be gathered into a project. You can have several projects, but this is that project about this problem. And then you can basically pass also a dictionary where you store all the important information you want to store. So here basically what I will do is that I will store all the hyperparameters I've used for that specific run. Okay? All right. So I will also give a name to this model. And I will store that there. Let's call it Potter GPT. All right, so the model will be model name. Then I have the batch size parameter. Then I have the block size. Then I have the size of the embedding. Then I have the number of training iterations. Then I have the learning rate. Then I have the number. Eval iters. Ok, voilà. Okay, so this is only initializing a process connecting to the platform and then waiting for the next instructions. And the next instructions you should add this case will be in the training loop where, okay, basically we'll use this if statement where we were evaluating every 250 iterations the loss and the validation. Instead of just printing these values onto the terminal, we'll also send them to 1db. Okay, so that's something I can do easily now by just using the log method, which expects as input a dictionary of stuff that you want to send to the interface. Okay, so here I will send the iteration number into variable step. I will send the training loss. Losses train, and I will send the validation loss. Okay. So now if I run again my script, you will see something a bit different. So you get these additional outputs, which are created by 1db. It says that I'm currently logged in, blah, 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 blah. It's starting a new run, giving automatically a name to that run. Okay, so it's a unique identifier with a number. Then it runs and then it fails because yeah, it should be validation, thank you, like this. So let's try again. Okay, now it's a new run, it's a new ID. You get a new identifier with a new number. Okay, otherwise, from the terminal it's still the same, but now if I connect to the interface, you see that there is this new thing, which is the current run, for which I get directly access to the losses as I train. Okay? But it's already completed. Okay? And now if I want to retrieve information about this, you see that we get everything that we stored. So the batch size, all the parameters are there. And that will be very convenient. For example, when you want to compare runs, you can go on this table. And there you see all the runs that I did for each configuration of the parameters, for each value of the losses there. So you can start sorting and trying to understand the effect of your hyperparameters, or quickly retrieve an old run, and without having to think twice, you know that, okay, for this run, these were the hyperparameters, everything has been booked for you, and you don't have to worry about that anymore. Okay? So really take the time to learn how to use this tool. It's time well invested. Just take 1 or 2 hours to understand the API, to read the documentation. If you don't do that, I can guarantee your experiments will be a big mess, and you will lose track of what you are doing, and you will not be able to retrieve, for example, hyperparameters that you have used to train this or that. All right, so this is done. This is done. Okay, one more thing. You can store loss values, okay, but you can actually store anything. So one thing I will also store together with the loss values are examples of generations of my model. Okay, so within the loop, I will also generate a few continuations of the sentences, and I will store them also on the platform. Okay, so not only I will have a quantitative way to evaluate my model, I will also have a qualitative way by just looking at the sentences that are produced, and I will have directly access to that from the platform. You can even, so this is convenient for text, but you can also send images. If you are building, for example, a generative model to produce images, you can also send images directly on the platform and see them directly on 1DB. Okay, but to do that, I will need to add a bit of code. So I will start from a few, let's say 5 prompts, and these 5 prompts will be the 3 first letters of some of the characters in Harry Potter. So R, R, Ron, Dom, and let's say Hag. Okay, for Harry, Hermione, Ron, Dumbledore, and Hagrid. Okay. Hopefully, if the model learns correctly, it should continue these 3 tokens, these 3 characters, by the names of the characters. Okay, so I need to transform that into a tensor of numbers. So for P in prompts, I call my encode function P. So now I have a list of numbers, and I put everything into a tensor like this, which I put on the device. All right? Should be correct. Yes. Then I produce outputs for each one of the prompts. So I call the generate function on the prompts, and I continue them for 100 new tokens. But these are numbers, so I need to decode them. So for O in outputs, so I have the output produced by the generate function, which is this batch of tensors. I need to convert each element to a list, then to call the decode function, which expects a list and not a tensor. And then I'm putting that into another list because of 1DB, like this. All right, and then now I will add to my dictionary a new variable that I will call sample, which would be a 1DB table where I will have as columns only one of them, which I will call samples, and I will have as data the output. Okay, so let's see if that works. Okay, so you have a new run 126. Okay, it's there. No visualization yet. That will come. Okay, there you see it. Now you have this new panel where we have 5 samples. And what is nice is that you have also access to the samples conditionally on the training iteration. So initially at iteration 0 before training, we get back these very random generations. But as we train and we reach the final iteration, we get something where again we start seeing groupings of letters into words, spaces, the correct frequencies of the characters, and so on and so forth. Okay? Questions on this so far? No? All right. Okay, and the last thing I will also do, even though if in this case it's not maybe that useful yet, but that's something I also really recommend you to do, is that these neural networks, you will have to train them for hours, if not days. So please save them. I mean, that seems obvious, but you have to write the code to actually save them once they're trained. Otherwise, if you want to look at more predictions or you actually use the network, if you have not saved them, you have to retrain them again and again, wait for a few days. Okay, so take the habit from the beginning to actually save the models. So here I will add some lines of code to do that. So I will store everything into a directory on the cluster. GPT, like this. And I will store checkpoints into the directory like this, and using the model name that I've set just above. Okay, so this is just the name of the path I will use. And then the only piece of code I need to add is something like this at the end, save model, which is very easy. I can just use the save method from Torch, where I save the model and specifically its state dict into a file, so the checkpoint. Yeah. Yes. Yeah, exactly. So I will show you after that how to basically reload these models. You need, of course, the file itself, and also you need the class to be defined within the scope of the program. Okay? But so now, where is this thing? So this is saved. This is there. So if I show you the content of this directory, okay, we have all these files already. But if I run it again, you should see after training a new file which should correspond to pottergpt.pt. Okay, so let's see if that works. Okay. And now I do ls, and you see this new file there, which corresponds to the model, the neural network that I've just trained. Okay? Do you have questions so far? Okay, so now we'll move on to the actual model, the decoder-only model. Let me just switch to that. And it's there. Okay, but I will just first go back to this notebook just to introduce the mechanisms we'll use, and then we'll port them again into the Python file. Okay, so there, yes? What do you mean? The 1 dB inside a notebook? Yeah, you could do that. But I mean, in any case, I would only recommend to use notebook to explore. Don't use a notebook for the actual thing that you implement. Otherwise, it will be a big mess. So yeah, it's a regular program at the end. So put everything into Python file, regular Python files. Your life will be much simpler if you do that. It's a good idea just to explore, and I use that a lot myself, but as long as you really want to, for example, every time you will want to train a neural network for a few days and have a few of them to try, if everything is in a notebook and you have to let the notebook run on your laptop or your machine, then you are risking the notebook to stop, and yeah, it's just a recipe for disaster. Okay. Okay, back to the model. This one. So far, even though we have already spent 2 hours on that, the only thing we have implemented is a simplification of this model where we say that P of W t plus 1 given previous word, given a prompt, which in this case already has been limited to the block size last element. So we have not 1 to t, but t minus k, where k is the block size, plus minus 1, plus 1, k is 1, something, it's not really important, up to t. No, there is a plus 1. Okay, where we say, and the only case we have considered so far is when k is equal to 1. Okay, because we said that the only information we'll use to predict the next token is the current token. Okay, of course, it would make much more sense to have a way to consider all the previous tokens. Okay, because together they form the context about the possible next tokens. Okay, so how could we basically aggregate all these previous tokens in order to predict the next word? So these tokens are represented by vectors of embeddings, okay? And I'm just trying to find a way to aggregate these vectors all together because I believe they will form a context which is more powerful than just looking at the last token in isolation. So how could we aggregate these vectors? Yeah.
When we have only 1 token, we are doing the same diagram because we have nothing more than this to proceed.
Yeah.
Then we concatenate the 2 strings, we use a trigram.
Yeah, but then it would, I mean, that means you would expect to see many combinations of these compositions of, I mean, of tokens to have big grams, 3 grams, 4 grams, 5 grams, and so on. So that would scale very poorly. So how can we aggregate vectors? So let's say I have 5 vectors of size 10, and I want to produce a context vector of size 10. Or I have 7 vectors of size 10, and I want to produce a vector of size 10, which will correspond to the aggregation of these 7 or 5 vectors. How could I do that? Yeah, I can just average them and say that the average vector of the tokens correspond to my context, okay, which aggregates all this information from these tokens. Okay, we could try to do that. Okay? So let's say, so that's something we'll do, and from which then we'll be able to derive the self-attention layer that we've seen last week. But let's say we have a batch of 4 elements, 8 tokens, and each token is already represented by a vector of dimension c. And just to keep things simple, I will say that each token is represented by 2 values. Okay? So then I instantiate just to some random values, btc, and I have something like this. Okay, so I have a tensor as expected, and the content would be something like this. Okay? All right. So the first idea we said, okay, I will aggregate this. So along the time dimensions, I want the context. For example, for this, so this is the first sequence made of 8 tokens of size 2. And I will say that the context for that we associate for the first token is the mean of the tokens up to that position. So in this case, that would be just that element. For the first 2 tokens, we will have the mean of the 2 token vectors. For the third token, we would have the mean of the first 3. For the fourth, we would have the mean of the first 4, and so on and so forth. Okay? So basically what we are seeing is that we'll say that the representation of the context for some batch element B and some position T in the sequence is a mean over the element in X for that position B and some of the tokens I, and the ones that we select are the one that goes from I up to T, okay, and then we take the mean of this, okay? So what I'm just writing there is just to say that what we'll store in this tensor are the context representations, okay, which will compute simply as the mean of the embedding vectors of the tokens up to T. All right? Okay, how would you implement that in Torch? Yeah. Okay, so we can be very inefficient and do a for loop, but that will be correct. So that's what we'll start doing. So we have a for loop over the elements in the batch. So we have B of them. And then we have a for loop over the positions. Then the previous tokens are the ones that go from 0 to T included. So it's X, B, T up to T plus 1. Okay. What's the dimension of this tensor? So it has a size of T, and for each token, a size of C. Okay, and then I'm saying that, okay, let's call it like this. So bow means bag of word. So it's the bag of word representation of X. And we say it's a bag of words because we just don't care about their position. We just say they are these words, they form a set, and we will aggregate them all together into a big vector by just taking their mean. Okay, and so what we do now is to compute the mean of Xprev, and we should do that over the first dimension, okay, over the temporal dimension, and not over the channel dimension. Okay, so now if I look at X0, which is my first sequence in my batch, and then I look at the backward representation of that sequence. Whoops. It should be B, T. Yeah, I should Xbow. Of course, I should initialize the variable first. So it should be a variable of size B times T times C. Okay, okay. And then now if I look at the first, I have this as an output, where you should see that the first row, so the representation of the token of the context associated to the first token only is the mean of the first token, so the token itself. So the first row here and the first row there, they are the same. Then the second row in the bag-of-word representation is the mean of the token representations in the sequence. So if you take the mean of plus 26 and minus 22, you get 0.02, and the mean of 1781 is in between 75. Okay? Then the third row is the mean of these three vectors. The fourth row is the mean of the first four, and so on and so forth. Okay? Okay. So now I will show you that we can implement the same function, but a bit more efficiently using matrix vector multiplications. Okay? And from there on, we'll be able to derive the self-attention layer. Okay. Okay, so we'll try to write this using matrices multiplications. So I will show you first the code and then I will explain. So I will compute a matrix that I will call wave for the weights. Okay, it's a weight matrix where I have first a matrix, a triangular, lower triangular matrix made of ones and of size t times t. So we have something like this. Okay, it's full of zeros above the diagonal, and otherwise it's equal to 1 everywhere else on the diagonal and below it. Then I will say that I will actually normalize the rows such that they sum to 1. Okay, so I would say that weight is equal to weight where I divide each row by the sum of its elements. And I do the sum on the first dimension, dimension 1. I keep the dimension of this. And now if I look at this, I have something like this, where now you see that the sum of the rows, it's equal to 1. First row is 1, 0, 0. Second row is 0.5, 0.5, 0, 0. 1/3, 1/3, 0, 0, and so on and so forth. Okay? And now if I have this, then I can use that to compute the mean of the first elements by just doing a product. Okay, so if I store the result of the product in a new variable xbow2, where I say that xbow2 is the matrix times vector multiplication x, and I look at the content of bow2, and I say I look at the first. Okay, you see that we get the same values. Okay, and you can check all of them if you want. So if we check if numerically all the values from xbow1, the first implementation, and xbow2 are the same, we'll get true. Okay, so they are really the same. Okay? All right. Now, if we look at this matrix, basically each entry tells us how important is each token to predict the next one. How important is each content of the context to predict the next one. And here we are just saying that all the tokens in the prefix, they are all equally important. Okay? I will just now rewrite this in terms of scores that will still implement the same logic, but without having them constrained within 0, 1. I will just let them be numerical values on the real line. Okay? And I will use a softmax then to rewrite then the implementation. So let's say I have, again, a lower triangular matrix made of ones, torch, ones, TT, Okay, so trill is equal to that. Then I now say that the weights, they are just made of zeros. Okay. And I will interpret the values now of this matrix as just like how important, again, is each of the token, but I will not have this constraint of having these values bounded between 0 and 1. Okay. However, I still want to have this interpretation that some of the tokens will not be used, and specifically the tokens after the current token, I cannot look at them, so they are not important for the context. And so therefore their weights, their scores, they should be the lowest as possible, which in this case would be set to -infinity. Okay, so I will just mask out some of the values. So everything which is set to 0, or everything which is set to 0 in the trill matrix, I will fill with a -infinity value. Okay, now if you look at this, we have that. Okay. Okay, and then to recover the previous implementation, what can I do? I can just softmax every row of this weight matrix. And I do that on the second dimension, so dimension 1. And again, I can compute the bag-of-word representation. Let's call it xbo3 for this third implementation as the matrix times vector product of weight and x. And if I check again if they are all close, xbo3, it should hopefully return true. Okay, so why have I decided to do something like this? It's because eventually I don't want the tokens to be equally important. Okay? There should only some of them, that's my hypothesis, are actually necessary to predict the next word. So I may have different scores for each token. Okay? So instead of having these values all set to zeros or to -infinity if the word is not allowed to be used at all, I want these entries basically to become data dependent. Okay, depending on the current context, I want the importances of these tokens to change to predict the next word. Okay? So let's do a fourth implementation. We'll do a data-dependent weighted sum. So we'll replace just the average of the token representation by a weighted sum, a weighted average, now where the weights, instead of being hard-coded as before, will be a function of the data. Okay, so let me just... I will copy this and just use longer vector representations of size 32, like this. Okay. So then I have this, like that. Okay, and so basically the trick now will be to replace this line by something which is not 0, but which is a function of x. Okay, we'll set the weights, the scores of the tokens as a function of the data x itself. Okay, and the way I will do that is by replacing this weight by, if you remember, an attention matrix. where we'll have the keys and the queries there, and then we'll compute the product of this to obtain the affinity matrix. Okay, so this is what we had there. There, okay, where we'll replace the weight matrix by this one, Q times K transposed. Okay. However, we still have to compute the Q and the K transposed, but we'll do that exactly as we did there by just saying that we'll derive them by doing by doing linear projections of the tokens. Okay? Okay, so let's do that. So I will first define a first linear projection as a linear layer that goes from vectors of size C and then produce other vectors, which could be of size C, but not necessarily. Usually what will happen is that we'll say that this mechanism will be embedded into a head in a transformer block, and we'll have, let's say, head size of 16. If you remember, that's something we'll do when we will implement the multi-head self-attention layer. I will also not have any bias term. Then we have the query, which again is the linear. It's a linear layer going from C to head size without bias. Okay. Then I actually compute the key value, the keys, by just doing a forward pass on that layer using X as input. And I compute the queries by also calling that layer on X. And then I say that my weight is the result of the product of these two matrices. Okay, so Q times K transposed, Q times K, but I need to transpose it. In this case, that would be transpose of the last two dimensions, because K is a tensor with 3 dimensions, and I need to only swap the last two. So you swap them like this. Okay, and now if I look at these weights, I will have something like this. Transpose. Okay, where now you see that the entries are not set to zeros by default. Runtime. Of course, that does not work, but that's expected. Up. Let me run this. Up. And this would be 4, which I will call just out like this. Okay, where now out the term has a size of 4 times 8 times 32. Okay, where 32 is again just the size of the embeddings that we had initially. Okay, even though we use lower dimensional vectors for computing the scores, the affinities, if you want, between tokens. We use a 16-dimensional space instead. We could have set that to something else, or even to 32. That's not really important. Okay? But what is really important now is for you to understand that these weights that we use to compute this average, now they've become data dependent. Okay, they are derived from X. Okay? Okay, so we are very close then to the self-attention, to the full self-attention layer. The only difference is that when we do self-attention, we are not aggregating the token embeddings, we are aggregating values that we've derived from these token embeddings. Okay? So in a regular full self-attention, what we would have is a third projection to compute values that goes from C to head size. And here we would have at the end, so the attention matrix would still be computed exactly in the same way. The only thing that would change is this last line here, where instead of multiplying weight with x, we first compute values that we derive from x, and then we say that the output is the product of these two. Okay, and then we have something like this. And now the difference is that the output, the last dimension of the output is 16, which corresponds to the head size that I've set. Okay, this one. Because now we are doing a weighted average over vectors of head size elements. Okay? Okay, one last thing. It's not exactly this. It's almost that. The only difference is that I've not implemented yet this division by the square root of the dimension of the embeddings. Okay, so that's something I will do. But to tell you and to give you some intuition about why this is really, really useful to do. So if you initialize, just as I did, your 3 projections, okay, what will happen is that the product, so the variance of the entries of the matrix will be quite large by default. Okay, so let me show you that. If I look at the variance, so if I say that I initialize randomly some vectors of keys from a Gaussian, for example, and I have b times t times head size element, then I do the same for some queries, which are just artificially created here. And then I compute the weight matrix as before, as the multiplication of the two. Transpose. -2, -1. And then I look at the variance of these 3 things. Q and weight. Whoops. Like this. You see that the variance of the elements of a vector drawn from a multivariate Gaussian, of course, is set to 1 by design. However, you see that the variance of the entries of the weight matrix is quite large. Okay, 17. Which means that these entries, and so remember, these entries, they will enter a softmax. So that means we'll have very small and very large values, which will push into a softmax activation function. If you do that, that's very dangerous because you will quickly reach the saturation regime of the softmax activation function. So if, for example, you say torch softmax of some tensor made of some values, 0.2 minus 0.3 minus 0.05 and then 0.05. Check dim equal 1 minus 1. Okay, so if you take a regular vector where all the entries are more or less on the same scale, you will get something like this, where also then the output after the softmax, they are more or less uniformly distributed in this case. However, now, if you keep the same value, but you just change the scale, for example, if you multiply them by a factor of 10, okay, you will get something quite different. all the entries will be close to 0, except for the one which was the largest initially. Okay, so 0.5 was the largest among these ones, and you see that it then obtains a value of 0.93, which is quite large compared to all the others, which are all close to 0. Okay, so for all these 4 entries, you are already in the saturation regime of the softmax, and it's only this one which will have an effect then in the weighted mean. Okay, so how do we fix that? When what we did in the course was to say, I will divide this by the square root of the dimension of the embedding. And so now if you say that you divide by that, so you multiply by the head size to minus 0.5, and now you will be recomputing the variance of the weight matrix. Okay, now you see that the variance associated to the entries of the weight matrix is set to 1, which will put you back into a regime where you don't have these huge variations, which will put you into the saturation regime of the softmax activation function. Okay? Questions? No? Okay, so let's take a break then, and let's say we resume in 10 minutes at 11:30. Okay, so we have seen that we can derive the self-attention mechanism by just starting from the bag of representation of tokens, which is a weighted mean. And if we say that now this weighted means, and specifically the weights in the weighted means, they become data dependent, then we arrive to the self-attention layer that we talked about last week. So now I will go back to the implementation of the model itself. I will re-implement this in a proper module, and then from there we'll continue building and converging to the transformer architecture. Okay? All right, so let's do that. Okay, so first of all, I will rename now this model to just transformer language model. Okay, this will no longer be a bigram language model. Like this. And the first thing I will do is to implement one of these head mechanism in which I will implement this weighted sum of the input tokens. Okay, so I will add a new class. So the idea is that I will be now defining several building blocks as NN modules themselves, which then I will reuse in the main class, the transformer language model class. Okay, and the first one of those will be a head module, which will implement the core attention mechanism. So again, this is something for which I need a constructor. I will also pass the size of the head. I will have to define a forward pass for that, which will take as input some data. Okay, so in a head, I need 3 layers: the projection for the queries, the projection for the keys, and the projection for the values. Okay, and from those, I will compute the attention matrix, softmax that out, and then compute as output the weighted average of the values. All right? Okay, so super.init like this. Then I have my first layer, which is the same as in the notebook. It's a linear layer that goes from now not C, but the size of the embedding, so an embedding, to head size, no bias for the linear layer. And I will have 2 similar layers for the queries and the key and the values. Query value, like this. And I will also implement these mechanisms where I will not allow the tokens from the future to have an effect on the current one. And so I will use this lower triangular matrix. And instead of recomputing this matrix at every call of the forward pass, I will just store it once and for all. And so that's something that you can do by registering a buffer, which is more or less like a constant in a module, which I will call trill. So this is so basically it's when you want to attach some PyTorch tensor to an NN module, but you want to say that these things, they are not parameters. Okay, so you should not train them. Okay, so they are fixed, and you can do that by using this register buffer method. Otherwise, it's the same. It's lower triangular of once, and now it's not over TT, it's over block size. Boom, boom, boom. Okay. Okay, then we have the forward pass. So what we want to implement is that we have a batch of tokens, and we want to produce the weighted representation of values associated to these tokens. Okay? So again, we'll have B, T, C for the shapes. We'll compute the keys, okay, by just evaluating the key layer on X. So that will give me a tensor of size B times T, one for each sequence, one for each token in the sequence, and of size H, the head size. Similarly for the queries. BTH, and the values I will compute them after. Then we compute the affinity, the attention matrix as the product of the two previous matrices. Okay, transpose -2, -1. We rescaled by the square root of the number of channels, so C. C up, like this. So now, what's the shape of this guy? So we are multiplying Q of size B, T, H together with the transpose of K, which is of size B, and then we have swapped the last one, H, T. So that becomes B, T, T. Okay? So we are computing in parallel for each element of the batch this T by T attention matrices. Okay. Then we mask out all the future tokens. Masked fill, self trill. We limit that to the size of the sequence, TT. Equal 0. And we pass instead minus infinity. This is still B, TT. We've not changed the shape. Then we softmax the rows. And we do that along the last dimension. Okay. Then we compute the values, which is given by self value on X. Then we compute the output as a product of the affinity matrix with the values, and then we return. Okay? Any mistake? Oh no. Okay, so what will we do with that? well, we'll use it. So we'll add a self-attention mechanism, which will instantiate by saying that we have head, and we'll say that the head size is equal to the size of the embedding. And when we do the forward pass, okay, what we'll do now is to say that instead of directly computing the logits from the sum of the two embeddings, we'll transform these embeddings using the head mechanism. And so we'll call the head on H, and then we'll use this new representation as an input to the final head of the network. Okay? And so now this should be of shape BTC. Yes. Okay. Okay, so let's train this new model now. So you see that the number of parameters has increased, only slightly in this case. We get already a lower training error, not by much, I agree, but it seems this has an effect. Okay, and the generations is still more or less of the same quality. Okay. So of course we are not there yet. What we need now to implement is the actual multi-head self-attention block, which is something like this, where we would have the input tokens that goes through a big block to produce a new representation, right? And what do we have there? We have first a layer layer normalization layer. Then we have the multi-head self-attention. So far we have implemented that as if we had only one head. So that goes in like this, but there is a skip connection also. Okay. And then we have, again, layer norm, followed by an MLP, the feed-forward neural network, which is applied in isolation to each token, or to each vector associated to the tokens. Again, there is a skip connection. And finally, the output. Okay? So this whole thing is what I will call a block. And we'll start by implementing this multi-head self-attention as just a list of heads that we run in parallel, and then we reconcatenate everything. And then we'll define a block. So this is already implemented in PyTorch. We just have to implement this forward pass where we concatenate all these elements together, where we have the skip connections. And then, if we want the full transformer network, what we'll do is that we'll repeat these blocks block 2 a few times, and then we'll have the final head to produce the output. Okay? That's the transformer network. which is what we had there. So it's almost this one, but simpler. So where we just have we don't have this encoder part, we just have the decoder. It's a decoder only. So this is implemented. We are about to implement what is inside the dashed rectangle, which is what I will call a block. Then we have the multi-head self-attention. It's already masked because of this thing with the lower triangular matrix. And then we'll have just a feed-forward neural network, an MLP, with the skip connections and the normalizations. Here what you see is that, and that's how it was designed originally, that the layer normalization layer happens after the multi-head self-attention layer or after the feed-forward neural network. But it has been noticed that if you put it before, it works better. So I will just stick to the modern version of the transformer. Okay? So let's do that. Let's implement the rest. Where is my... It's there. Okay. So first thing, I will implement the multi-head attention. And you will see that it will be quite fast from now. So I will have, again, a new class which inherits from the same neural network module, for which I need, again, this self, head size, def, forward, self, x. Okay, and what I just need to do is to instantiate in parallel several of these head modules. And I will be running them in parallel and then concatenate everything at the output and projecting into a common dimension. So I have the constructor first. Then I have the heads. And I will just say that this is a list of modules. So it's a module list where the list that I pass. So I will have to specify the head size, yes, but also how many heads I want. Okay. And so I will create a list for all the heads that I want, where for each I will instantiate the head object of size, head size. Let me... Okay. Then I will have a projection, a linear projection, remixing everything together, which is linear, like this, of size embedding, and producing vectors of the same size. And then the forward, so for each head H in the heads list of modules, okay, what I can do is to just evaluate these heads. I put everything in a list. Okay, so I'm just iterating in Python over the heads. For each of them, I compute the output. So I do forward pass. Okay, and then I will be concatenating everything along the last dimension. Torch cat of this along the last dimension, so -1. Okay, so each head will produce new vector representation, where these vectors, they are of size, head size, and then you get, let's say you have 4 heads, then you get 4 of these vectors, and then I'm just saying I will concatenate all these vectors. Okay? All right, then I do the projection, and then I return. Okay. So already what I can do is to replace this head by a multi-head. Is this correct? Head size, multi-head. And I will say that I divide, so to keep more or less the processing to be of the same amount, I will say that each head in my multi-head self-attention will have a net size of n embedding times the number of heads, okay, which I still have to specify, by the way. Where is it? And head. Okay, let's say it's 4. Like this, and I have 4 heads like this. Okay, so that should work. If I try to train this, okay, there is a mistake. Line 89. Should be better like this. For now, I'm keeping the network to a small size. Once we'll have implemented everything, then we'll scale up in terms of number of parameters. But so now you see that we have 4 concurrent heads. We don't have that many more parameters, but you see that already we reach a lower training error than when we had only 1 head. Before, in the previous iteration, we reach, for the lowest training error, 2.43, and we are already below 2.30. Okay, and you see for the first time we had the completion of H, which is this. So I provide just one first symbol, which is H. And in this case, you see that already the model has completed that by array, okay, which does not seem very random, okay, but really tied to what it has learned from the training set. Okay, so we have now the multi-head. Now we need to define the feed-forward neural network, and once we'll have that, we'll put everything into a block. Okay? Let's do that. Feed forward, and then module, boom, def init. Self, what do I need? I need the embedding size. I need a forward pass. Super, not init. Okay. So how would you implement an MLP, the MLP block? Yeah. Yeah. And yeah. That's what we'll do. And so we can do that by just using the sequential module where we pass just a bunch of layers. Sequential beam, where we have that first linear layer, which takes as input vectors of size and embedding. So this is quite important, and which can be confusing the first time you try to understand the transformer architecture is that these tokens, they are processed individually in isolation by this feed-forward neural network. The MLP does not take the entire sequence as input. It takes just the tokens in isolations. Okay, and just modify that representation. Then a ReLU, and then produce a new representation of the same size. Okay? Boom. And finally, well, of course, we have to define a forward pass where we just return the output of the forward pass of the network module. And with that, and now we'll define the block class. Okay, init, check, self. So in a block, we'll define the size of, we'll provide the size of the embedding and also the number of heads. We'll define a forward pass. Check. Okay. So as before, I will say that the head size is the size of the embedding divided by the number of heads. Then I need to define all these components that you see in a block. So the two layer norms, the multi-head self-attention, and the feed-forward neural network. So multi-head, where I have the number of heads, beam, and of size at size, like this. Yeah. Then we have the feed forward. And I need to pass the size of the embedding, like this. And then we have the two layer norms. And the second. So this layer norm layers, they come with parameters, so that's why I need to instantiate two of them. And voila. Okay, and how do we implement the forward pass? Well, I will just work with the variable h, which I will use to compute the output of the block. So initially we have that h is equal to the input. Then we have to pass that to the first layer norm. Okay. Then we pass the output of the layer norm as an input to the multi-head self-attention. Then we pass that as an input to the second layer norm. And we pass the output of the second layer norm as an input to the feed-forward neural net. Tac, and we return. Okay. I will add the skip connections later. I just want to show, because I want to show you that they will have an effect on the quality of the results. Beam. And finally, I can move back to this part. So now I will replace this multi-head by the transformer itself, or rather by a list of blocks, where I will say that, again, I have a sequential model where I will say a certain number of blocks, let's say 3 of them, where I will pass n embeddings and heads. Let's say I set it to 4, and I put another block like this. bim, bam. And now I replace this by blocks. And voila. Tac. Of course. Okay, so now we have 26,000 parameters. Do you have questions so far? Okay. So now, of course, the bigger and specifically the deeper the network, the lower it will be to train them, to train it. And now it's already quite big. We are chaining 3 blocks, each made of layer norm, multi-head self-attention. So this thing is itself running in parallel, several heads. Then layer norm, an MLP, and we repeat that 3 times. And we have a final projection at the end. Okay, so meanwhile, I can maybe already start implementing the skip connections, which I would need in the forward pass of the block. So how could I implement the skip connections? Where basically what we want is to have this. So we compute from this value, we traverse these 2 modules, we get some outputs, and then we want to have also this connection where the original input would be summed to the output of the multi-head self-attention. Yeah. Yeah, so we can. I mean, it's really trivial to implement. So I will say. So I will rewrite first my code in this way. Then I remove this, and then I rewrite this in this way. Okay, it's equivalent as before. But now if I want to go over the layer norm and the self-attention with the skip connection, I'm just saying that H should be the sum of this block plus itself. And we have a skip connection. And the same for the second skip connection over the next 2 elements of the block. So if I save and retrain, so you see that the error reached 2.34. And now the error should go much lower. Okay. So as soon as you have a deep neural network, if you don't have these skip connections, then the gradients will tend to disappear. Even if you initialize everything properly, use ReLU, it will be difficult for the network to train properly. Here you see that after already 1,000 steps, we are below the same network without the skip connections. Which train for five times longer. Okay. Then, if I'm sticking to the regular implementation of a transformer, okay, there is the question, so how can you make this transformer, this architecture bigger? If you want to put more capacity, what should you increase? What do you think should you increase? Yeah. Yes, we can increase the context size. Anything else? So one thing we can do, I mean, one thing where there are a lot of parameters is actually the feed-forward neural network, okay, which will be transforming these tokens in isolations. And usually what we do is instead of going from C to C and then C to C with a ReLU in between, we upscale the dimension of the tokens from C to something larger, and then we go back from that dimensions to C. Usually we use an upscaling factors of 4. And so that will add many, many parameters. So you just remember that before we had 26,000, and just by increasing this 4 for the intermediate hidden representation in the feed forward, now we've doubled, more or less, yes. Also, let's look at the generation of the previous version of the network. Now you really start seeing words already. Hard, you, add, off, it, stain. These are regular words that we've managed to learn. Okay, so now we start having a network which has understood the concept of what is a word. A word is made of characters, but not any character in any random order. There is some structure, some distribution over these combinations of characters that you should use to build proper words. Okay, and already with this network we have that. We are of course not there yet at the level of producing correct words and then from this word producing sentences which make sense, that I agree, but we are starting, remember, at the level of characters. Okay? And the network is only reading 7 books from which he is learning that. Okay, so this is done. Layer norm is done. Tac. So this is okay. Okay, so meanwhile I will clean up a bit and add the number of blocks as an hyperparameters together with the number of head. So we had 4 before. Okay. And now so the multi-head and heads is done. So here it should be an head. Let's call it like this. Okay, and if I want to parameterize also the number of blocks, I should replace this actually by having blocks, which is NN sequential, taking a list which I unpack, where I instantiate block and embedding and head. Like this. Check for in range and blocks. Right. Should be correct. Okay. Also in the original architecture, there is a final layer norm just before the head of the network. So the fully connected layers that we have at the very last. So I will add also that, the final layer norm of size and embedding. Tac. And now I will so this is still correct, but I have the self layer norm f of h like this. Okay, should be okay. All right. So let's see if that works. We should have just a few more parameters because of the layer norm that I've added. Yeah, so that works. Okay, so that's done. Then, before scaling up, I will add the last ingredient, which is a dropout layers, which we use. That's something we'll see later on, but which I will use anyway. So a dropout layer is something that takes as input a vector, x, okay, and remove at random elements of this vector, okay? So it's setting to 0 some of these elements, 5, where maybe this one will be set to 0 and this one will be set to 0. If you call again that dropout layer on the same vector, then it will randomly mask out other elements. And why are we doing that? It's to basically reduce overfitting or improving generalization by forcing the remaining part of the network to be robust to missing information in the vectors. Or a side effect of that is that the information will be more or better distributed along all the elements of these vectors because they have to resist this dropout mechanism. Okay, so we introduce, in a sense, redundancy in the information that you pass along instead of maybe overfitting and having everything into one element. Okay, so we'll do that for the head module. Self dropout equal nn dropout, and the dropout factor we'll use dropout is something I will define above. Tac. By the way, let me also add here now and blocks and head and dropout dropout. Okay, so I have this new thing there. And usually we do a dropout on the weight matrix, on the attention matrix. Self dropout await. Okay, so that's the first. We'll do that also for the multi-head module. Dropout. Dropout. And we'll add that here. Voilà. And for the feed forward, we'll do that too. Dropout. Tac. Okay. Where is this? So 4. Of course. Hop. Okay, so previously we reached an error already below 2, where we started seeing words being formed out of characters, actual English words. We'll not see much an improvement because of these dropout layers, okay, to be honest. If we want to see an improvement, now we need to scale up the dimension of this architecture. And so this is what I will do. So I will basically increase all these numbers. I will consider larger mini batches of size 64. I will have a larger context instead of just 8 characters, which is really tiny, because even words can be larger than 8 characters. I will increase that to, let's say, 256 characters. I will use embeddings of size 344. I will use, is it already this one? Yeah. I will use 6 blocks, and per block I will have 6 heads. So if we divide 384 by 6, that means each head will deal with vectors of size 64. I will iterate for the same number of iterations. I will evaluate maybe less often because that will be more costly. Okay, and very importantly, because now I will have many more parameters, I will reduce the learning rate. Okay, so basically the recipe is that the larger the number of parameters you have, the lower your learning rate typically should be. Okay, so in this case I will reduce it to this magic number, and then I will save and try that again. And you see that we have run this thing a few times now. If we go back to this, okay, we have all these other runs, which I can plot, including the ones that crashed because of my mistakes. Okay, but you see that everything is basically recorded for you. So again, just to stress that it's very convenient. Here we can also see, maybe for this model, yeah, the kind of improvement we get qualitatively as we train. So this is at the beginning, in the middle, and then if we go to the end, okay, we get something like this. You see that some of the words, you would expect them to be easy to guess, okay, like dumb to be completed to Dumbledore or Ag to Hagrid, but this remains difficult for this network. And one of the issues is the very short side of the context we used for training this thing. Okay, all right. So now if I saved, yes. So now we should have many more parameters. Okay, so now we have 10 millions of them. It will take longer to train. And this one is running on a very old GPU, so actually it should be much faster, but it's because the GPU is quite old. So let's see a few steps. Okay, but you see that we arrived to an implementation which counts just a bit more than 200 lines of Python. And that's actually a transformer, okay? That's a transformer network. If you scale that further, if you scale this constant further to larger networks, that's exactly the kind of networks you have behind ChatGPT and other systems. It's exactly these things. Of course, you need more than that to have like an actual chatbot to which you can talk to, but really the core of it, the pre-training phase of these systems is exactly what I've implemented this morning. Just much bigger neural networks. You would have in the hundreds of billions of parameters. So here it's tiny neural network with only 10 million parameters. I'm talking about neural networks that are, again, 10,000 times larger than that, okay? And these networks are not trained on just 7 books. They are trained on the entire internet several times. They are not trained on one GPU. They are trained on entire data centers full of GPUs, okay? But really the core recipe, the core architecture is this architecture. With some variations, I agree, but really the core of it is that. You see it's taking quite long to make the first step. Well, let's wait for the first at least. Do you have questions? Okay, so about actual chatbots. So you have this very huge pre-training phase, which involves this architecture. But there are other components that you need to actually make this system as good as they are. So there is a lot of fine-tuning, which also happens to make these agents, this language model, something that you can use as conversational agents. So basically, they are further fine-tuned on examples of conversations which have been annotated with scores of quality. Okay, so there are different strategies that you can do to implement that. And so this is really a part which is really important to improve the quality of these systems. Here it's just basically at the end of the training what we'll get. Okay, we see the first step. we'll get a language model which can just generate sentences. Okay, then if we want to use that as a chatbot, we need to fine-tune and also to set the prefix, the prompt that we want to continue. That's how they work, actually. Every time you type something to ChatGPT or any other tool, there is a prompt already in the conversation, which we call the system prompt, which is not shown to you, which informs the system about what it is, how it should respond, many instructions just explained in full English. Okay, and then basically the language model, it's as if it then was playing a game, a role-playing game, where it impersonates this thing and will just produce the rest of the conversation, which is consistent with these instructions. Okay, but at the core, it's just something that samples these tokens one by one, but in a way which is plausible with respect to the previous tokens, and also with respect to the conversation that you also inserted yourself in between your question, for example. Okay, let's see the second step. And you should see after 1,000 steps that it's much better than, at least in terms of the loss, than what we managed to reach. The lowest was 1.99. Yeah, so the tokens I've used, they are not very good also. I mean, it was just for the exercise this morning. It's easier to explain things at the level of characters. But that's something I will actually show you later, I mean, very quickly. If you change the way you tokenize, basically you increase the size of the vocabulary. That will also have a huge effect on the number of parameters. And that's usually much more powerful because to produce a coherent word at the level of characters, you need to make many predictions coherently and correctly. So as soon as you make a mistake, then you diverge into something which does not make sense any longer. If you are allowed to directly produce at once parts of a word, then it becomes easier to scale to sentences and longer pieces of text. Okay, because the atomic words or tokens that you have produced, they already contain much more information than characters. Okay, you see second step, I mean, the step 1000, we have reached an error of 1.6. And if you keep training, that will just keep, this will just be better and better. If we look at where we are, okay, we are already there in the loss. And if we compare the quality of the predictions, yeah, we already get something which is quite good. We get almost always English words. We start maybe seeing sentences or compositions of words that maybe could look like sentences where you have a subject, a verb, some stuff, a point, and then you start a new sentence. This is because now we have switched to longer context. Okay, we went from 8 characters to 256 characters, and within this context, then you have the opportunity to make or produce coherently sentences. Okay. When it comes to context that you can achieve now with regular chatbots, you can scale to hundreds of thousands of words. Okay, you need implementation tricks for this to happen because really the bottleneck is that the context size will induce this matrix, which is quadratic in the size of the context. Okay, so this is the main bottleneck, and going to larger and larger context size induce problems because of the attention matrix. Okay, So let me stop this. Okay. And I just want to show you this, and then that will be it for today. So these are two models that I've trained a few some time ago, but which are larger, even larger than this one. But other than that, it's the same model. So this one counts 30 million parameters. Okay. I will have this. And you see, okay, no, I should run this. Okay. But you can recognize the implementation. I've not changed anything. It's more or less the same. There are a few slight variations to really fine-tune the results, but the idea is really the same. And I will show you that we can generate text. And I will start with this sentence. Excited, I reloaded up, which is a sentence which appears exactly like this in the book. And so after this, so the second line is something which is produced by this language model. So you see sentences that grammatically they are correct. Semantically, do they make sense? That's another question. But you see that the network has already learned the concept of more or less a sentence. We can recognize subjects, verbs, stuff. But of course, now what is missing is the meaning. Okay, they don't make any sense. If I try again, because of course now the generation is random, and that's also why every time you ask the same question to ChatGPT, it answers differently. It's because at the core, it's just drawing these tokens randomly, proportionally to their probability as you compute them with this neural network. And here you see that the sentences, they don't make much sense. And that's also an issue because of the limited size of the context. It can be quite coherent within the window of the context, but for longer sentences, you will maintain local consistency, but you will not achieve any long dependencies between the words that are produced. So this is for a first version, and an even larger version here, which would work at the so it would. So this one, by the way, is still at the level of the characters. And now if we change the tokens to some parts of a word by just basically considering pairs of characters, more or less. So I will load the model. This one has about 70 million parameters. And if I start with the same prompt, you should see, I mean, it's difficult to say, but you should have more consistency, longer consistency, because the tokens are longer. They are not anymore at the level of characters. You see, for example, that the quotes, they are put, there is a beginning and the ending quotes. And if you wonder if it has memorized the training data, that could happen. Looked up at the dark ceiling. So if I open the file, oops, sorry. Dark ceiling. just looked up at the dark ceiling, but you see it does not appear in the training set. Okay, and then you can continue and generate any text that you want of any length. You see, it works more or less. But now I suppose that you can imagine how it works in practice if you just scale everything to bigger neural networks, bigger data set, bigger compute, then you arrive to language model that are ready to be used or almost ready to be used as chatbots. Okay? Questions? Nope? Okay, then thank you. That's it for today.